Section 516 is called dynamic braking. So this is a very important section. Make sure you dig in on this and make sure that you understand what's going on with it. It's a fundamental concept, a fundamental application in electrical machines. It's used in many applications you're already familiar with, and we'll explore some of those as we go through this. But yeah, make sure you get this and make sure that you understand it, and we'll walk through it together. To begin our discussion on dynamic braking, let's make sure that we understand the associated figure with this. This is figure 517A, and let me just point out a few things to you. Of course, this is the source voltage. The source voltage is applied directly to the armature through a switch that we designate. That's what that is. That can open and close. And so, that's the first thing that I would show you. The second thing is, of course, this is our armature, and this is the voltage that's developed across the armature when it rotates. That's that part. This would be the armature current here that's flowing. And then also, we know this is a shunt connected DC motor because we have the field here, right? The field here that's connected in parallel with the armature, okay? So that makes this a shunt connected DC motor. And let's see, what else? This, of course, again, this can open and close. That's just a big throw switch. And we can open this up and we can actually, close it to this resistor. And that's where we're going to learn about this whole idea behind dynamic braking. So that's a little bit, on the figure. And then we've got three figures that are going to represent this concept of dynamic braking. So as we're looking at this initially, we look at figure 517A, and this would just be, this is just the normal operation of this DC motor. Everything, here's the polarity of the voltage across the armature, so forth and so on. So this is just normal operating conditions. Now, what we're going to do is we're going to go from 517A to 517B, and what we did here was we opened the switch, okay? So we opened the switch and basically disconnected it from the source. Now, although disconnected from the source, the shunt field is still connected. So it is still producing the magnetic flux that causes the voltage to be developed across the armature. Now, this armature is slowing down due to friction and what they call windage losses. But it's slowing down, but it's still rotating. And it's still developing a voltage, again, because this shunt field is still connected to it. Now notice the polarities on everything, on the source and on the armature. And notice, if I go back to this slide, notice that the current, is going in that direction when it was connected. And of course, there is no current flowing actually through the armature when it's disconnected. It's not connected to anything, so there's no current flowing in that condition. So in the third position, I'm actually closing the switch to this resistor. Now, initially we had this, and current was flowing in this way because it was connected to the source and current was flowing into the positive terminal. Now, this armature was always rotating. It was always receiving flux from the connected field. But now look what happens. The polarity on the armature is in this way. So what's going to happen is the current is going to flow in this direction. Now, that is a change of current direction. And whenever you have a change of current direction, what happens is you get what's called a reverse torque. So if you thought about the torque initially as a positive torque that's caused by the interactions of the magnetic fields and the current, now think about the current changing direction. And so there's an actual reverse torque that occurs. And what that's going to do is that's going to slow and work against the rotation of the armature and bring this machine to a controlled, rapid, smooth stop. And that is the dynamic braking effect that's occurring. What we can do in the dynamic braking application is we can choose a value for this resistor so that we can choose a value for this R that's connected to, so that the braking current, which we're calling I2 now, the braking current, because it's a reverse and reverse torque current, we can select a resistor such that the current that's flowing is about 2 times the full load current of the motor, and the initial braking torque is then twice the normal torque of the motor. He goes on to tell us in this dynamic braking application that the motor slows down gradually, and that the E sub O corresponding decrease in current, it occurs, in conjunction with the speed decrease, the current decrease. But consequently, the braking torque becomes smaller and smaller because the current is getting smaller and smaller. And so the speed drops quickly at first, and then it's more slowly as it proceeds through. And actually, we're going to be able to model this speed decrease as an exponential function, okay? And it's going to look like, if you remember, maybe you remember the effect of discharging a capacitor, and it looked like this, across there. We're going to actually see that same effect, this exponential function, with the dynamic braking concept. And so, we'll get into particulars. The speed decreases by half in equal time intervals. And he shows us this curve here, and we'll explore this to a little more depth later. But we're going to define this T sub O, and after one of these time constants, the speed is decreased by half with dynamic braking, and then after another one, half of that, and by after another one, half of that. So you get this exponential function. And as we're in the middle of a COVID pandemic, and we've talked about exponential curves, those of us that are in this world, we want to be able to speak this language, right, and describe this. And I'm looking forward to the time to where this COVID curve starts looking like this curve here for this dynamic braking, right? That's what we're hoping happens. So anyway, we don't want to see this. That was a digression. I'm sorry. That's what we talk about in 2020, isn't it? All right. So that's 516 dynamic braking, and then in the next section, we're going to explore this concept of plugging and see how it differs from dynamic braking.